So I'm using the following half an hour to introduce our latest work related to torsion and also the combined torsional behavior of FRP-reinforced concrete members. The work is also done with Professor Wei Xue and also several PhD students. Today's talk, I will include in the following 6 sections. First is a brief introduction, and everyone I think is very have a very clear background on the why we're using FRP in the concrete structure, especially for FRP reinforcement. The basic issue is that the corrosion of a traditional steel reinforced concrete structures. The latest data, although it is have more than 6 years ago, but recently we can still find that corrosion economic loss is still relatively higher compared to the other like timber structures. And especially for infrastructure, besides the seaside, the corrosion, especially for the steel reinforcement, is also have taken a large percentage. So based on this background, we found that using FRP reinforcement to replace steel reinforcement is a good solution, because the research already and also the practice already demonstrate that. And the research also started as early as 1960s, and in China a little bit later, since 1990s. And when we start to study the torsional behavior of FRP-RC structure members, we also have done a survey, and that found that extensive studies until now will include the mechanical behavior of FRP reinforcement and the bond performance, and also for member, it includes the fracture, compression, and also especially for shear behavior. And looking for the publication, we can also find that even recent 5 years related to FRP reinforced concrete, the publication is still higher. So it seems the research is still a hot topic. And also, if we're looking for the application, we can find that, and it is highly correlated to the development code. And since 1990s, we can find that the application has been increased, especially for the bridges, marine infrastructure, and some part is for the underground structures like pipe, and also some special purpose buildings, especially for that anti-magnetic functions. And so from this figure, we can see that the code developed first is in Japan, and also in US and in Italy and in European countries. And in China, the national code is started 2010, and we also have the industry code typically for the bridges. And now we have latest version in Shanghai standard that is also a newly developed in the recent 5 years. And for the application, we can find that especially in the North America, we have a lot of application in bridges. And in China, our application also have bridges and also have some wharf. Especially latest, we have done under the National Key Research Project, we have applied the thermoplastic FRP reinforcement in the wharf structures. So that is application. We can also find the application development also correlated to code. And the code, we also survey that from Japan to US and even in UK. And even in Egypt, we have several design code for FRP-reinforced concrete structures. And in China, we generally have three different codes or standards. First, in national, the latest updated one is for since 2020. And then the industry, that code, as I mentioned that before, that is for bridges. And the latest Shanghai code, which is developed under the leadership of our research team. And it included, we have compared to the bridges code and also national code. We found that for a reinforced concrete structure and even the pre-stressed concrete structure using FRP reinforcement, we have included in Shanghai code, we have included the most comprehensive design scenarios, including torsion, as I will talk today. This is the first Chinese code which involving torsional design, although it is just for pure torsion. Later work we will also done for the combined torsional design method. So that is for the latest situation in abroad and in China. And I'll go back to the today's topic is related to torsion of FRP-RC members. So this research started 3 years ago. And we at that time, we founding that limited studies on torsional behavior, especially for pure torsion, especially for combined torsion behavior. At that time, even no study published, we can found that is related to like torsion and shear combination. Very few studies related to the bending and torsion behavior. And also we can know that if we our audience is working on this research field, we know that FRP is elastic material. So for torsional behavior, it will completely have the complete different torsion mechanism to the steel FRP steel reinforced member. So and also for no matter buildings or infrastructures like wharf or bridges, the torsional scenario is very common. So we needed to develop the design method for these cases. So that is our work, which is under funded by Chinese National Science Foundation, and also the center is for Nexel. This is for non-metallic excellence and innovation center that are funded part of a work. So generally, in this, our group's research first started from the FRP reinforcement the strength model, especially for stirrups. And then we come into the members' behavior, including pure torsion, combined shear and torsion, and even combined with bending. And then to design, to develop the design method. So in this today's talk, we generally cover this as 4 content. First is the stirrup behavior, and then going to pure torsion, shear and torsion, and bending torsion behavior. Okay, so first, stirrup. The background actually is very simple. Actually, we know that FRP stirrup, which is quite different to the steel, because steel stirrup have identical strength to the longitudinal reinforcement. But for FRP stirrup, because the manufacture properties, it will causing the reduction of strength in the stirrups. It generally will accounting for 20 to 60% of longitudinal bars strength. And also, we have, since 2008, the FRP product standards have been carried out in US, Canada, and other countries, are generally focusing on FRP longitudinal reinforcement. Only part of the codes related to the bend strength that we can say that is related to stirrup. But for stirrup long-term behavior, I think right now after we developed the new product FRP product standards, there is no other code standard product standards related to the long-term behavior of FRP stirrups. So that our work, including the 3 parts. First is reliability. Why we do this work is when we have in the past we have done a lot of band strength tests for different kinds of FRP stirrups, including the stirrup types. Like here, I have a combined closed spiral and closed one. Actually, the previous 2 combined closed and spiral is have a similar manufacture method, only cut a partial from the spiral, then go into the combined closed stirrup. And then the commonly considered feature is radial versus the diameter, the ratio, and the diameter of stirrup, and the fiber type, and also the test method. Until now, the standard test method for stirrup, we have 2 types. They are all coming from both coming from ACI standard, one B.5 and B.12. So we also done different type of test method. And when we want to determine more precise functions or formula to predict the band strength, we are finding that you will see that figure, large standard deviation from the prediction. And no matter how many parameters we can involve, the deviation is large. And also it has an issue is that the factor still very complex for the FRP. And also there is no very standard manufacture method or regulation for this kind of products causing this issue. So how we do the design, so we come into this study is we want to develop the distribution model for the strength rotation for the FRP stirrup. So first we done the Pearson sensitivity analysis. We still finding that primary correlation factor is still the radial versus diameter ratio. Also, it also have a relationship to diameter, to fiber types, to the test method, but the measure of primary factor is still coming from the radial versus diameter. And then we doing the hypothesis test and finding that for the database we collect from our research group and also from international globally, we found log normal distribution is the most optimal model for the FRP stirrup, no matter which kind of fiber or which kind of types of stirrup. And also within the conventional radial ratio that is from 3 to 5. We finding that this range is will be commonly used in the structure. And also we finding that the formula here showing that is commonly used in many national code in ACI or in Canada or even in Italian. So their petition for the strength rotation ratio, which is conservative because reliability rate for this calculated value is only between 20 to 40%. And if we using the data, if we want to make sure the rotation rate is under 95% guaranteed rate for different radial ratio, for 3, 4, 5, the rotation rate will below to 35%. So that is for the reliability analysis. And then we go into long-term. One is creep performance because GFRP stirrups is still the most commonly used stirrup, and also the alkali resistance FRP stirrup. And for the creep behavior, we have done the research test and including the band ratio, radius under the same diameter, and also the stress level, and also fiber content, because we're using two different products stirrup. Their difference is fiber content. And the test results show that first, this is we're using B20 test result because we can involving the concrete bond effect. And the typical creep behavior, as shown in this figure, is have typically 3 stages. Primary stage is when we have during the short duration have a increment, and then we go into the steady distribute of strain, and then when during right close to the rupture, we are finding that the strain have a abrupt increment. And also, we were finding that based on the different, when we vary the stress level, the duration of the creep, it will be increase. And also, we will say that creep rupture time decrease exponentially with increased stress level. This is showing the reduction of the stress level versus the time, rupture time. It's for 2 types of FRP stirrups. And based on this behavior, we developed the creep strain model to evaluate the long-term straining behavior for FRP stirrup. And also, we do the prediction of rupture strength ratio prediction, which is correlated with time and also correlated with a radial diameter ratio. And you will finding that first, this is a creep rupture reduction factor for GFRP longitudinal bar. So we can see that this is for 3 different diameter, and we're finding that the creep rupture factor reduction factor have a difference to the longitudinal bar. So this is the first latest finding. And for the alkali resistance, which also is important for GFRP stirrups, so we done the durability test, and we put in the alkali environment in the water, and have different exposure time. The longest time is 1 year, and also different temperature. The test method is similar is the same as that used in the FRP longitudinal bars. So we can finding that also the exposure time and also the temperature increase will increase the reduction of the strength. Here is the band strength, and also it will finding that the tendency is vary with the time. And when we look into more detailedly, first is the macrostructure, which is similar as that observed in the longitudinal bar. The pole structure or pole volume will increase. It is causing the moisture absorption also rate increase significantly during the before half a year. And when the exposure time start from the 183 to 1 year, we're finding the moisture absorption rate will come into steady. And this phenomenon is similar to longitudinal bar, but the standard duration is later for FRP stirrup is later than the FRP longitudinal bar. In our group, our research finding that for longitudinal bar, the moisture observation steady time is right after 90 days. That is can be attributed to the band zones macrostructure, which is different to the longitudinal bar. So based on the result, we also develop the strength degradation model. and which is based on the linear functions. So we also predict the environmental reduction factor for 50 years for GFRP stirrups in the alkaline environments, and we also compared to the longitudinal bars reduction factor, which we see that the factor is much lower. And this is for the reduction for the band strength of GFRP stirrups. So from the longitudinal behavior, no matter creep or alkaline resistance, which our conclusion is that they have a significant difference to the longitudinal bars for GFRP. So when we studied, finished the study of FRP stirrups, and now we come into the members that is for torsion and first, pure torsion first. And we also finished the experimental study, numerical model, and also developed the calculation method for the strength. For the test, actually, we have done 11 beams, which have rectangular cross-section, and 5 specimens is without stirrups, and 6 specimens with stirrups. The parameters show in the screen, that is including stirrup ratio, longitudinal ratio. And here I want to mention that this test, especially the following the test with combined torsional loading, we have developed the test system, and we have collaborated with a testing company to make sure that the actuator, multiple actuator can synchronize during the testing. And also we developed the torsion-free support under the beam, which can free extension, in the longitudinal direction, and also free torsion when the beam under twist. And so for pure torsion, here you will see that there are P1 and P2, there are 2 actuators, and they were synchronized, that in meaning that the force between these 2 is have sharing the same ratio, FP1 equal to FP2. So make sure the pure torsion exerted to the beams. And also here we know that for FRP-reinforced beams, because FRP is elastic, so it will have over-reinforcement or the rupture of FRP. So here we finding that we also designed that the beam under torsion following these 3 different category, the failure mode. And also we realize these 3 failure mode in our final test result. First is failure mode in the beam without stirrup. And the failure is due to the concrete spiral cracking. And after crack, the load is decreased immediately. And we also finding that the spiral cracking have been found in 3 surfaces, and in the another long side surface is have the concrete fracture, that is a fracture of concrete strut. That is for beam without stirrup. And also most important is the spiral crack angle. And we found in that first issue is that right now we do not have a specific or constant regulation for the crack angle. How to calculate it is using the tangent angle at the center of beam or using the secant. There is no consistent conclusion. So we also calculate these 2 kinds of angle separately. And we finding that if we finding that the tangent angle at the beam center, it is very close to the theoretical calculation based on the elasticity mechanism. And we also found interesting phenomenon, that is, as we know that for torsional behavior, although we do not have a stirrup, but maybe the longitudinal bar will have contribution for torsional behavior. But we finding that if we increase the longitudinal bar ratio or longitudinal bar's area, we are finding a very clear tendency that is reducing the torsional behavior. So this is not the same as we found in the steel RC beams. The reason we found later is that we found that because the GFRP bars shear modulus is quite lower than the concrete. And here we show that this is a GFRP. CFRP is close to concrete, and still the shear modulus is much higher than the concrete. So that means when we involving the material have lower shear modulus, that is weaken the concrete material, concrete section. So that is why we increase the longitudinal bar ratio will decrease torsional behavior. This is a new finding. And then we further studied the beams under stirrups, with a beam with stirrups. And similarly, we have found the spiral cracking, and we have found the two failure modes. One is stirrup rupture, as shown here at the band strength zone, band zone, and also concrete crushing without FRP failure. So this is two typical failure mode. And when we look into the more detail, that is cracking angle, and here we see that from this figure, with different longitude stirrup ratio, we can see that the spiral angle is close to 45 degrees. And this is say that from the over reinforcement failure mode, we say that FRP stirrup rupture to the concrete crushing failure, we can simplify. We can consider the spiral angle is 45 degrees when we do the calculation. And for the twist, torque and twist angle behavior, we can see that first, with the increase of the stirrup ratio, the deformation will increase. And also when we compare to the steel, here showing the comparison with the steel FRP-RC beams with the same stirrup ratio. First, this is a concrete crushing failure, and we can reaching the similar capacity of torsion. And also because steel have larger shear modulus, as I mentioned before, so the stiffness will higher than the FRP-RC beam. This is very easy to understand. But we can see that when we consider the twist deformation, we found that the steel RC beam is lower than the FRP RC beam. So see this figure, the blue one is steel, and the red line is FRP RC beam. So it has larger deformability. This is also a very interesting finding from our test. And also we have found the relationship with capacity with stirrup ratio and the longitudinal ratio. And later, we also evaluate the stirrup straining behavior in FRP-RC beams. And also finding that because the twist angle, it will involving all legs of the stirrup. So we can see that the shorter or longer leg of stirrup have straining, and the ratio is around 40 to 60%, quite still lower than steel because steel have elastic plateau. And also here showing that the rupture strain highest is around 7,000 epsilon. So this is quite close to the result in the shear behavior. And also we found that longitudinal bar strain is rather lower than the rupture. So in that way, in FRP-RC beam, we will not achieve the failure mode of rupture of longitudinal bar. So only stirrup rupture or concrete crushing. And then for actual elongation, we can also find that the modulus stiffness of the longitudinal bar and stiffness of the stirrup all have effect on the actual elongation. Then after test, we developed a numerical model, which is based on the rotation angle softened truss model, which is first developed by the Xu and Mo, and similar assumptions that be used in the steel RC beams. And here we just involving, first is the failure criteria for different two-type failure mode. One is concrete crushing and another is FRP stirrups. And right now, the FRP stirrup ratio strain is only developed by the average value from the test result. And for the constitutive model, first, the tensile constitutive model, which is govern the post-cracking stage. And we also developed normalized tensile stiffening coefficient for FRP and even for steel RC beams, because the longitudinal or Young's modulus difference will causing different tensile behavior after cracking. So we have finally normalized this tensile stiffness. We can involve in both steel and FRP. And then we also introducing the more appropriate softening coefficient for FRP-RC beam. And as we showed here, this is a combination between steel FRP and GFRP based on the same reinforcement ratio. We are finding that GFRP have more longitudinal extension. So it means we can also see this figure. The compression behavior of strut will be affected by the longitudinal straining. This straining also we're finding this figure, scattered figure is for steel, and this orange figure is for FRP. So elongation in FRP is much higher than a steel. So we're finding that several published or proposed softening coefficient is not fit for the FRP RC beams. So based on the current data, we're finding that the coefficient proposed by Blaby and Xu, their coefficient is more fit for the FRP RC beams. So when we involving these three true constitutive model and the governing failure mode governing coefficient, and we can finally will predict the FRP GFRP RC beam on the pure torsion, no matter the capacity and also the complete progress during the load. And even the stirrup, longitudinal bar, and concrete surface strain quite close to the test. So based on the numerical model, we also done a lot of parametric studies, over 700 beams on the pure torsion, involving different ratio, different concrete strengths, and also develop the features which how it influenced the capacity, especially influenced the balanced ratio, which we is balanced the boundary ratio for over reinforcement and the stirrup rupture failure mode. So based on the numerical model and also based on the test result, we finally developed a calculation method. And this involving the concrete contribution and the stirrup contribution for torsion. And this is the stirrup failure. And we also have involving the compression failure limit. Here we haven't been extended further. Actually, we can further improve this formula because over reinforcement failure mode is also can be involved in the design method. And here we more focusing on the stirrup failure mode, and here based on test result and also numerical result, we regress the coefficient 5.1, 5.3, and also for the compression limit for 5.3, and also the balance ratio will check the failure mode. Here, the alpha, as I mentioned, our test result observation is 45 degrees. So we can simplify this alpha equal to 45 when we're using the design method. So later, I will in the standard chapter to further introducing the design method. Here is just the calculation method. Okay, so this is the evaluation. Our proposed approach is have higher, more close prediction to the test result and even the numerical result. And then we come into the shear and torsion, and we have done 8 beams with shear and torsion. Here also different stirrup ratio, and here is torsion shear ratio from complete. Here is shear, and ultimate is infinity is shear, is meaning the torsion, pure torsion. And here we see this is illustration for the test stirrup. Here we have 3 actuators. They are also synchronized by the system. So P1 and P2, P3 is for torsion. And for the middle force, this force is control the shear force, and the ratio between the P1 and the P2 to control the torsion and shear ratio. So this is a test table for all the specimen we involving different shear torsion shear ratio, and also evaluate the stirrup capacity effect for the certain shear and torsion scenario, loading scenario. And the failure mode, which is also our curious. First, we have finding that this is a different for pure shear, and for torsion shear ratio is for the highest 1.5. We're finding that the compression plastic hinge forms on the shear flow superposition side, but the cracking initiate at the shear follow reduction superposition side, and for the concrete cracking for specimen without stirrup only cracking, we only typical cracking observed. But for beam with stirrup, we have multiple cracking, and we also found in the partial over reinforced failure mode, that is stirrup rupture, and also concrete crushing, we also can find in this type of testing. And also see that the cracking angle for pure torsion until to the pure shear, the angle is ranging along this value range. This is for pure shear, and this is for pure torsion. And further, we're finding that the behavior of torsion and also the shear behavior, and the most important is the interaction curve. Here is interaction curve from the pure torsion to pure shear, which is along this behavior. And we can compare to later I will showing how the correlation to the steel interaction curve. And also the stirrup rate strain, we finding that when the shear force increase, the long leg strain will increase a lot. That is very consistent with the stressing mechanism in the shear and in the torsion. And also, we're finding that this is a different type of scenario, and we found in the rupture strain ranging from the 7,000 to 10,000. This is rupture strain, which is higher than the limit strain in the code for shear. But this is a static value. We haven't encountered the reliability behavior. And now here I want to show you that based on our study test result, we found in the interaction between shear and torsion here showing that this is a data scattering here, and also including our numerical result, which is between the interaction curve for steel RC beam, and also and this is 45-degree line is for elastical theoretical results. So that means the elastic behavior of FRP have significant effect on the shear and torsion interaction. And now, last part is for the beams under bending and torsion. Also, we interested about the interaction behavior of these two loading cases together. And here, we have done 12 beams under different parameters, stirrup ratio, and most important that is bending torsion ratio, for pure torsion, and for higher bending bending torsion ratio, and also longitudinal bar, and compared to the steel FRP-RC beam, steel RC beams. So this is the stirrup image illustration. Here we also have 3 actuator, and this is have the beams, distribution beam to causing this region is testing zone, have the pure torsion and also pure bending. So it causing the complete the bending and torsion mechanism during the testing zone, within the testing zone. And for the failure pattern, we also finding that the cracking phenomena is significant different with the change of moment torsion ratio. When pure torsion actually is a constant diagonal cracking, and when the moment increase here, you will see that the initiation is from the bottom, and then going up is in inclined cracking. And also the plaster hinge line or zone for lower moment torsion ratio is at the side, I mean the long side surfaces. When the moment ratio increase, the compression zone will come into the top, which is also similar as our theoretical analysis. And for the beams, previous is for beam with without stirrup, and for beams with stirrup, the phenomenon is similar. And the only difference is we can finding that more complicated failure mode will be observed for the FRP-RC beam. That is, stirrup rupture can be observed, and also for this concrete compression can be observed for lower moment torsion ratio. For higher bending control, that is also top concrete crushing, like what we've observed in the fracture design behavior in the FRP-RC beams. And for the behavior, here is a torque twist angle showing here, and also we are finding that with the increase of bending, the torsional twist deformability will increase, but the capacity will decrease. And looking for the fracture behavior, here is the figure for the load, center load, and the deflection in the center. We also finding that similar behavior like the fracture behavior, but more flatter, I mean the deformability. But also when the stirrup longitudinal bars increase, have significant effect on the fracture capacity, which is similar at that observed in the fracture design. So this is for the beam without stirrup. For with stirrup, similar behavior also can be seen. First is the torsional behavior will increase with the stirrup increase, but also when the bending increase, the deformability of twist will also increase. And here for the fracture behavior, here with increased bending, it will have higher fracture load and a higher deformability, and more elastic behavior or linear behavior will be observed in the fracture behavior compared to the twisted behavior. So based on the test, also we are interested about the interaction curve. First of all, beam without stirrup, we're finding that longitudinal bars effect will not significant for the increment of the portion. But this ratio have a significant effect in the steel beam, steel RC beam. So this is first phenomenon. Second is for beam with stirrups, you will see that for stirrup rupture and further is compression in flexure. The interaction curve looks like this. First, increase the capacity of torsion, and when bending increase further, it will decrease the torsion. And for partially over reinforcement, this is for concrete crushing. This is for FRP stirrup rupture, and still we are finding the increment due to bending in the torsional behavior. So this is a general conclusion or finding from the beams under bending, torsion, and also previous is shear and torsion. And for these two combined loading situation, the numerical study and our calculation method is still under work. So if we have chance later in any conference or webinar, we will want to share our later works. And last, I want to introduce a little bit of the standards related to our previous two works. First is about the stirrups, and here, as mentioned before, this is FRP Chinese FRP stirrup standard, which is also the first product standard for FRP stirrups. And here, we involving the fiber content, modulus for stirrup, and band strength, especially to regulate the minimum rotation ratio, and also the bond strength, because we need to make sure it have the contribution to the shear, to the torsion, and then most importantly, we involving the long-term coefficient related to alkali resistance and creep performance. Here we introducing the limits for the alkali resistance reduction and for the creep performance. Here is following the 90 days under standard test method for FRP longitudinal bar. And for creep performance, also under the standard creep testing for longitudinal bar, FRP longitudinal bar. So this is the true limit ratio we have regulated in this code. And for the members, as I mentioned, there are several codes internationally, especially for Canada code, have developed the torsion for FRP-RC members, but they do not involve in the concrete contribution for the torsion. And also, this calculation is completely based on the steel RC beams. So based on our previous calculation method study, we developed further for the design method, which is following. First is involving the coefficient for alpha and beta, accounting for concrete contribution, the stirrup contribution. And most importantly, here I want to show this slide, because following the Chinese code related to reliability design for the brittle failure members, and under this regulation for the alpha and beta, we can achieve the target reliability index for torsional capacity within the regulation for brittle failure members under our Chinese national code. So here we further compare to this red line is our code's formula, and the blue lines is the Canada code's equation. We can find that our proposed formula is having we call the moderate safety margins, especially for lower stirrup ratio. So this is our work and research work, and our research work coming to the showing in our Chinese code. And last, I want to share our group's work for the application based on research and also the collaboration with companies. This is a typical project we've done. For this is a seawall, complete using FRP reinforcement, including the stirrup and longitudinal bar. And totally, we have finished the demonstration application with over around 20 kilometers for this seawall. And also we have done a demonstration project using seawater, sea sand concrete with FRP reinforcement. And this column shown here is also have torsional scenario. So this is for a small project beside the sea. And the last is our latest work. Last year, we finished the application or demonstration projection within the wharf deck and the fender block using the thermoplastic FRP, which is developed under by the our national key research project. Okay, so this is all the content I want to show with audience, and thanks for your attention, and question is welcome.